In the last video, we looked at how to visualize electric field and just kind of what the electric fields look like in different situations with different charges. In this video, we're going to look at some of the calculations that go along with electric fields. So first off, let's take a look at our equations that we have. By definition, the electric field is force per unit charge. That's how an electric field is defined. But we can actually manipulate that formula a little bit to get another electric field equation. So if we take Coulomb's law, which we've already studied, and we go ahead and that's the electric force. If we divide it out by the charge, we're going back to the definition on number one, force per unit charge. What you have left is the electric field, so that cancels out one of the charges. So number three there, that's another equation for the electric field, K Q over R squared. So you would use number one, the equation number one, in a situation where you have a uniform electric field. A common place for that is if you have two parallel plates that are charged. In between the two, you would have parallel lines of electric field. That's a uniform electric field. Number three's equation you would use if you just have a point charge. So it'd be like the charges that we looked at with Coulomb's law, but we'll just look at one of them and we'll talk about the electric field surrounding it, which then would be the electric field would go radially out from the charge. So then we have a changing electric field by distance. Notice number one, it doesn't matter how far away you are since it's uniform. Number three, it does matter how far away you are. Okay, so I have a few practice problems to go along with this, just to get some of the calculations in here. Number one, we have a 0.9 gram balloon with a charge of negative 75 nanocoulombs is located at a distance of 12 centimeters above a plastic tube that has a charge of negative 3 nanocoulombs. Apply Newton's laws, haven't seen those too much lately, to determine the acceleration of the balloon at this instant. So ultimately we're looking for acceleration. In order to find the acceleration, we have the mass, so we really just need the net force, and then we can use F equals ma. So that's our strategy. So to begin with, let's start with the force diagram to see what we have here. So we've got the force of gravity and we have the electric force. We don't know which one's bigger until we put the math in, and we don't know if they're equal. I assume they're not equal or they wouldn't be asking us for an acceleration. But we'll have to calculate each one. So here's our gravity force. So we're just going to do mg. That's pretty straightforward, and we've got that gravity force down. I didn't put the negative sign on here because we usually like to look and see what directions things are before we do that. So I'll add that on the next slide. So now we'll find the electric force. In this case, we do have two charges. So since we have two charges, we can use Coulomb's law. So we put that in the equation, and we get the force, the electric force, and that's going to be upwards. So now we have our up force and our down force. We can go ahead and find the net force, up plus down, and this is where I made the down negative to find a net force there. So now we can go back and we can use Newton's laws to find the acceleration. So F equals ma, here a range for acceleration. So we'll take that net force, divide it by that very small mass, and we will get an acceleration, which because the force is so small, the mass is so small, it still ends up being a decent acceleration. But you can see that the electric force did actually slow the force of gravity as far as the acceleration goes. So there's one example of kind of a charge problem. That one didn't directly have an electric field in it, but it's the kind of problems you're going to see in this section. Question, how could you find the velocity of the balloon at a given time? Well, you could use any who cares equation depending on the information that they give you in the problem. So the answer would just be to use a who cares equation. So second practice problem. So they've given us a little picture in this case. Sphere 1 carries a positive charge of Q equals positive 6 microcoulombs. Again, pay attention to all these prefixes on the charges. They do make a big difference when you do your problem solving. So we've got our positive 6 microcoulomb charge there on the origin. What is the direction of the electric field at point P, 0.6 meters away from the origin? In this case, it doesn't matter how far away P is from Q. The direction of the charge is going to be the same. The direction of the electric field. The direction of the electric field is always based on the direction that a positive test charge would go if placed in that field. So remember, a test charge doesn't actually affect the field. So the test charge is just going to go the same direction that anything would, that any positive charged object would in that field. So in this case, since the test charge is positive and Q is positive, it's going to push to the right towards P. So if they had given that same question and P had been on the left, then it would be, you know, to the left from that direction because it would be away from Q. What is the magnitude of the electric field at that point? So this is where we're going to start using those electric field equations. Now they're talking about a point. Since they said they have a point and we know the distance of that point, we're going to use this equation with the r squared in it. So we just pop in our numbers here. We have the same K. We've got our charge that was given, and we get an electric field. They're often large numbers like that, so if you get a decimal for an electric field, that's where I would be cautious. I'd be concerned about that. They're usually, if they're not in the hundreds, they're usually like this, where they're very large. Okay, so next part. So we have a test charge of Q equals 1 microcoulomb and the mass 2.5 grams. It's brought from infinity. They sometimes use kind of silly language like that. Yeah, I don't know why. And place it at point P. So now they're actually just telling us that point P has a charge of positive 1 microcoulombs, and they gave us its mass. So what's the direction of the electric force on Q due to charge big Q? So this one, we can just say that because they're both positive, it's going to be a repulsive force, so it's to the right. If they had given us that charge as well, here they say it's a test charge, so it should be positive, but if they had given us a negative charge, then it would be to the left. What is the magnitude of the electric force on charge Q due to charge big Q? So here we're looking for force. We do know the charge of each, so we could use Coulomb's law. However, we also already calculated the electric field. So you could use either of these two equations. The one that looks easiest to solve to me would be the second one, so that's the one that I used here, but you would get the same answer regardless of which one that you use. So we do have a small force then, and then it would also be to the right since they're both positive. Part E, what is the acceleration of charge Q at the instant when it's released from point P? So back to the whole acceleration question. So we can find, we already know our net force from the previous problem, so we're just going to use F equals ma. Rearranged for A, and we have our 0.15 from the last slide and the mass that was given, and we find our acceleration. That's a pretty high acceleration to the right. That's it for that one. So practice problem number 3. So here we have a wall with a negative charge distribution producing a uniform field. So this is the same thing. Sometimes they would say that is a charged plate. They just mean something long and flat that has a charge. The nice thing about that is that that's when you get those uniform fields. So we don't have to worry about distance. The field would be the same regardless of the distance that you are away from that. So we have a small sphere of mass 10 grams and a charge of 90 microcoulombs attached to one end of insulating string. They just mean that the string isn't going to carry charge, and it's 0.6 meters long. The other end of the string is attached to the wall. The uniform electric field has a magnitude of 500 newtons per coulomb. So that's what we know so far. Here's a little picture. So what is the direction of the uniform electric field? Okay, so again, even if they hadn't given us Q at all, so we didn't know that Q is being pushed away from the wall, that doesn't have anything to do with the problem. We see a negatively charged wall, so we know that if we put a test charge, that the test charge, which is positive, would be attracted to the wall. So that means the field has to go to the left to attract it to the wall. So regardless of what Q is doing there, it has to go to the left. That does tell us, even if we knew nothing else, that the charge on Q must be negative in order for it to repel. So that's something you already know. Okay, so what is the direction and magnitude of the electric field on charge Q due to uniform electric field? So again, uniform electric field tells us we're going to go to this equation, which is kind of handy. It's pretty easy to solve. And they already gave us the charge. So we pop that in, 0.045 newtons to the right. Okay. Oh, and by the way, I should have said that. The electric field here, the reason it says to the right is because that charge is negative, so you know that force has to be to the right. I think I kind of already mentioned that. Oh well. Part C, draw a force diagram for charge Q. This is actually very similar to the force diagram we did in class when we had the balloon and we stuck it to the wall. So it's something like that. You have tension that follows the string. You have an electric force out. We have gravity down. The one in class, we kind of talked about there might be friction there. In this case, because the string is the only thing holding it, that's all we have to deal with. So a straightforward force diagram there. Calculate the angle between the wall and the string. Well, if we have our force diagram and we break that angle tension up into x and y components, you can see that the electric force must be equal to the x component and that the y component must be equal to the gravity force. So that allows us to know two parts of the triangle already, and we can just use the inverse tangent then of the electric force over the gravitational force. So we do that, and we find an angle 24.7. So remember, again, whenever you're doing angles in physics, you do need to make sure that your calculator is in degree mode. Ooh, that's the last one. I guess that's it for this video.